we're going to take what we already know and run with it. In other words, we're going to do more and more complicated versions of finding derivative functions. Okay, so I'm going to give you a function just to get us warmed up. And we're going to find its derivative. Now, remember the rule, it's called the power rule. So put it up here just to remind everybody what the name is. And the power rule says the shortcut is multiply by the power and reduce it by 1. So you get 12x cubed. Multiply by the power and reduce it by 1. And what does the number 7 get you? What's the derivative of 7, which is what we call that process?
Nothing.
Nothing.
Zero, nothing.
Zero,
Yeah.
nothing. So just don't write it. Agreed? Very comfortable with that? Shortcut. Let's move on to some more tricky ones and maybe change the variables. This one is a version in question 3. They haven't changed the variable yet, but I'm sure I'll find one if I keep looking. Now, if you want to find the derivative, right, which is essentially the formula that will allow you to find the slope of the tangent line, even if the power is ridiculously big, the rule still applies. Multiply by the power, reduce the power by 1. Okay, what will the derivative of negative x get me?
-1.
That's it. And doesn't the number plus 7 get you nothing? Now, I'm going to write down a sneaky question to try and catch you up. And I am warning you, this is a trick question. And I'm going to do the first bit. If you find the derivative of t squared and you use the power rule, you get 2t. So here's the trick question. What is the derivative of 4 squared?
0.
I think you said 0. Is that correct?
Yeah.
Yeah. Does it matter that it's written like a square? No. Isn't it still a number? In fact, isn't it just 16? In fact, if I had written 16, you wouldn't have had a problem saying 0, agreed? Now, suppose it wasn't that guy. Suppose it was pi cubed. What would the derivative of pi cubed be?
0.
Still 0. Isn't pi just 3.14? Isn't pi cubed just some ugly number that I couldn't tell you off the top of my head? 29-ish, right? I know that you've seen exponentials, but just for completeness sake, what would the derivative of e to the power of 3 be?
Also 0.
Right. So isn't the moral of that story, I don't care what kind of number you are or how that number is written, aren't you still going to be 0 when you differentiate me? So 4 squared, e cubed, square root of pi, 1 over pi squared. Aren't they all numbers? And so they're all going to have a derivative of 0. Just a little side issue. Let's chuck in a fraction.
Well, Professor.
Question.
Could we do a derivative from the homework I was having trouble with?
Is it from this section?
It was from derivatives and the rate of change.
Okay, sure. Why not? It's
the derivative of the square root of 3 minus 22x.
Oh, that one you would have to do using the limit as x tends to a. Okay?
Okay, so you can't use a shortcut on that one then?
No, not yet. But in about a week, I can show you the shortcut on that.
Okay.
So that's why that one caused you so much trouble. Okay, this fella is going to be 9/4 x squared. Take away 4x, add 3. We're still on the power rules. So you multiply by the power and you reduce the power by 1. And you get -4 and that gets you nothing. And you will type that in and WebAssign will hopefully say you're wrong. Because there is a little bit of style points that you can do. And I see some nods. Can you see what the problem is? What you need to write to us? So what should this be written as?
9/2x minus 4.
Right. So, just, what am I getting at? You could be doing the question totally correctly, but you haven't made it pretty, right? Style points. And so you'll look at it and they'll say it's wrong. And you're going to think, well, I don't know how to do the power rule anymore. I thought I did, but this question proves that I don't. And that's not what happened. What happens is you didn't realize that 18/4 could be called 9/2. So just, to be on the lookout for that. Now, as I said, we're going to add some new guys to the list. I want to keep on power rules, but uglier power rules. So this is a version of question 7. And z to the -3, take away z to the half. And we're going to differentiate this using the power rule. Now, have you noticed that this is a -3 power and this is a half power, right? And we did some of them last week. The power rule doesn't care, isn't it? Multiply by the power and reduce it by 1. So this guy is multiply by the power and reduce it by 1. Are you happy about the -4? Right. Now, multiply by the power and reduce it by 1. What do you get if you take this power and reduce it by 1? What's the new power?
-1/2.
Correct. Now, in style points, there is make it look like the original and factor the heck out of it, right? That's the only 2 rules that we have right now. Isn't this like the original? You see, it looks the same. I mean, they're both ugly, but that's the answer. If, however, I'll pick a different question. If you got a question like this, right? They could have gave you that question. Before you try the power rule on that, wouldn't you have to rewrite it as powers? And then you could differentiate it. And I've picked a question that's, for all intents and purposes, identical to the one that's above. But that would not be considered the final answer. Aren't we to use style point rule number 1, make it look like the original? Do you see that doesn't look like the original? So what I'm going to do is I'm going to take that negative power and call it that. And I'm going to take this negative power and call it that. And then I'm going to take that half power and call it that. So in some of these questions, do you see that you may have a lot more work to do, even though it's virtually the same as that question? Isn't that question good to go, one answer? Whereas this question, you had to turn it into a power, right? Do the differentiation and then make it look pretty. So 2 questions may look very similar, but require a lot more work in one than you do in the other. That one's fine. And since we're on that, let's try question 9. If I'm going to differentiate this function, I need this to be written as powers, don't I? So what power of t is 1/t better written as? What
Use
power
the
of,
negative first.
I agree, and 1/10 cubed. 1/t cubed.
T to the -3.
Agreed? Are you happy with you have to do that before you can even do the power rule? Right? You can't do the power rule on that. Even if you wanted to, whatever you wrote down would just be wrong, right? You need to convert it into this. Now we can do the derivatives. Multiply by the power, -1, and reduce the power by 1. So that's the new power. Multiply by the power and reduce it by 1. Now, for style points, don't we have to convert it back to looking like the original? Agreed? So what would this guy be if you wrote it to look like that?
-1/t².
And then -3 over t to the 4. So are you comfortable with this algebra that seems to be cropping up a lot, where powers have to be turned into, 1/t³ has to be turned into a negative power, or the square root of t has to be turned into a half power? Let's do a square root one. This is a version of question 10. Okay, this one I hope doesn't catch it out, but you never know. Hard to tell what questions are going to catch people out. What do you get if you differentiate the square root of 3w? I don't think this should catch you out, but the fact that you're thinking about it might mean that it looks weird to you.
Just the square root of 3.
Yeah. If it was 5w, you wouldn't have had a problem. Wouldn't you just say 5? And if it was 10w, wouldn't you just say 10? And if it was the square root of 1,000,000 w, wouldn't you just say a square root of 1,000,000, right? And 0.1 w, wouldn't you just say 0.1? Isn't it just a number? Now, what do you get if you differentiate negative square root of 3?
0.
0. Don't you get 0 for any kind of number? No, as long as it's a number, isn't its derivative 0? Even something like negative the square root of 3 is still a number, right? You could do it in your calculator and find out what it was as a decimal. That's the end. That's the answer. How about this fella? Well, you got to turn both of these guys into, in this case, fractional powers, right? Both of them. I'll take I think the easier of the two. What would the cube root of x look like if you wrote it as a fractional power?
1/3 x.
Okay, like that. What would 1 over the square root of x look like if you turned it into a power of x?
-1/2 x.
Just a -1/2, right? Now, once you've got it in that format, then you can do the power rule. Multiply by the power and reduce the power by 1. Multiply by the power, and if you take 1 away from that, you get -2/3. And then you should look at that and say, does that look like the original? Well, the original had square roots and cube roots in it, so no, it doesn't, which means this has to be, what I call style points. I would start by recognizing that negative powers can be changed into that. You comfortable with that line? That a -3/2 can become this fraction, and that a -2/3 power can become this fraction. So far, so good. Now, that's better, but not perfect. This is going to be perfect. X to the 3/2 is the square root of x cubed. That's how you turn fractional powers back into radicals. In this case, x cubed inside the square root. What would the second one get you? What would a 2/3 look like?
Where's X squared?
And there's style points, right? Would you agree that looks like the original? And we're done. We haven't seen one like this before. So treat this as a new problem. Any suggestions what to do with this? Because the way it's written right now is not going to be a power rule. I can't really do a power rule the way it's written. I'll be able to do a power rule later, but not right now.
You've gotta do the what, distribution, the 3 cubed times 3 and 3 cubed times 4.
You nailed it. That's exactly. Would you agree that that's pretty obvious how to do it? You agree now it's easy, right? It wasn't easy the way it was written. So when you look at a function and you think, nah, I got to do something with this. This isn't, this doesn't work. Foiling was a good move in distributing. So when I do its derivative, I get multiply by the power, reduce it by 1, multiply by the power and reduce it by 1. What about style points? Can I do anything to this? Remember, there's 2 rules for style points. Rule number 1, the most important one, because that's the one you almost do all the time, is make it look like the original. And wasn't the rule 2 factor the heck out of it? Can you see anything you can do to this one that would fall into either of those categories?
Factor out 4x squared.
And if you did that, you're left with an x add 3. So that, I think, if I'm certain, isn't this the first time we ever needed to factor anything? Weren't most of the questions either the answer was good or you made it look like the original, right? You did some extra work on it. But this is the first time where you had to actually factor something. It happens. I'm not going to do 13 except the first line. If you want to differentiate that guy, that isn't really the form that it's useful in, right? I don't know how to differentiate things that look like that. I only know how to differentiate t-squares and things like that, right? So what should I do here?
Expand it and then do the FOIL thing.
Right, and you're going to trust me on this. You get that guy, you get that guy, and then you get that guy. And can you imagine now that that's going to be very easy to differentiate? Would you agree there's nothing much happening after that? It's A of r is pi r squared. Wouldn't that be the formula for the area of a circle of radius r? Wouldn't that be the formula for it? Pi r squared, right? Let's differentiate it. Multiply by the power and reduce the power by 1. Oops, there we go. Lost on my screen for a minute. Do you recognize the formula 2 pi r?
Yes.
What is it, the formula for?
Circumference of a circle.
Right. So we had the area of a circle and I differentiated it and I got the circumference for a circle. Now that could just be coincidence, right? Just happened to be, that's what it is. It's not actually. And the reason is that there are many ways of thinking about what a derivative does. We've focused on the slope of a tangent line, which it does do that, but it also tells you about rate of change. And you might say, well, how does that come up with a circumference of a circle? Can you imagine you've got a circle and it grows bigger? Right. So isn't the rate of change of a circle how much that circumference is? Can you see they're kind of connected? Don't circles grow as the radius grows? Don't circles grow by circumferences worth? There's a very unscientific way of saying that. So doesn't it kind of make sense that the increase in area would really be like adding on, you know, like if I made that 1 unit long, wouldn't that area be the same as the circumference of the circle? There is a lot of formulas that you'll find in your physics and chemistry equations and mechanics and all sorts of things. If you take those functions and differentiate them, you will find that you've got a new formula which is also being used in your chemistry, your physics, or your mechanics, because the derivative can be thought of as the rate of change of the original function. I think that's kind of helpful. I'll try one. Does anybody recognize this formula? I don't know. Anybody seen a formula that looks like that?
Is that kinetic energy?
It's the distance traveled by a moving object, right? So S of t is the displacement, and it's u naught the initial velocity. If you differentiate this formula, you get u naught plus at. Isn't that the velocity of a moving object whose initial velocity is u and acceleration is t? You had the kinetic energy formula. Let's put that one, k of t. Well, it won't be volume, velocity. Isn't that the kinetic energy formula, right? Or one of? If you differentiate the kinetic energy formula, you multiply by the power and reduce it by 1. M is considered a fixed mass. You get mv. Don't you call that momentum, I believe? So if you take the formula you know that only has one variable, v or t, and you differentiate it, aren't you going to get another formula that's probably useful in that same field? Let's move on and see what other fun stuff we can find to find derivatives of. I want to find, oh God, that's a good one. Anybody who can get this question correct without any help from me should really take over the rest of the lesson. Now, I don't need the entire answer because I don't know the entire answer yet. I have to work on it. But would you agree that this fractional formula, the function, is impossible to do with a power rule? It's just not written down as 5x squared plus 3x to the half, you know, that kind of look, right? That's the only ones we know how to do. Right? Any suggestions? Come on, impress me here. Something algebraically to do with that to make it closer.
The conjugate method?
Times
Oh.
the top and bottom.
Yeah. The conjugate I
Fine.
totally understand, but I think I like the next one. Right. Somebody said something about times the top by something, which I like, because that's actually what I want you to do. Now, I'm going to call this guy x to the half, and I'm going to call this guy 9x. What might you rewrite 4x squared as? Because I think that was close to what I wanted. And then I'm going to do it a slightly different way. What would you multiply by?
4x squared.
4x squared, yeah.
1/4 x to the negative 2.
You nailed it. Right, 1/4 x to the negative 2. And if you do that guy, you will get this guy times this guy, which is the number 3/4, and this guy times this guy is the number 9/4 x to the -1. And then you can differentiate it. I'm going to show you a different way of approaching that. Hopefully, you deserve 2 bonus points for that one. I'm going to take this and I'm going to split it into 2 distinct fractions. And then I'm going to take this guy and call it a half power. And although I don't need the 1, I'm going to put it in for emphasis. Can you remember when you had powers of x on the top and bottom? Wasn't the rule take the first one and subtract the second? So won't this guy become 9/4 x to the -1, right? 1 take away 2. And this one will become 3/4, and a half take away 2 is -3/2. Do we see those guys? And I don't know what happened here. That half turned into it. So forget the answer. There's the right answer. And now you can differentiate. Multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. Make it look pretty. And make this one so it looks much more like the original. That was a horrendously ugly question. You agree? Let's do another one. Because I think I screwed up there. That half turned into a 2 and that made that one bad. So here's another question. Like 15. It's going to be 4, the square root of x, plus 5x squared, all divided by 4x cubed. Right? And I'm going to take this guy and make it into powers of x so I can use the power rule. So I'm going to take this 4 square root of x and divide it by 4x cubed, and the 5x squared and divide it by the 4x cubed. I'm going to convert that into a half power and leave this one alone. Okay, the 4's cancel out. X to the half on top being divided by x to the 3 in the bottom. You take the top power and subtract the bottom, and that ends up being -5/2. You've got 5/4. Top power, take away the bottom. This one gets you 5/4 to -1. Can you follow the algebra that I used to convert this ugly fraction into 2 distinct powers of x? See? And you can now differentiate these guys. Multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. So we have now differentiated. If you want to make these look pretty, i.e. look more like this, you make the negative power into a positive power on the bottom. You make the negative power the positive power on the bottom. That one's good now. This one, to finish, has to be called the square root of x to the 7. And this one is okay. Do you follow the algebra that's being used in this question? Are we comfortable? It's quite messy, but that's kind of the strategy you should do for questions that are written like this. Separate them. Find out what the equivalent fractional powers of x are. Do the power rule, and then spend a lot of time making it back. Technically speaking, isn't that the only line where I did any kind of calculus? Wasn't everything else algebra? changing things from one form into another and back again. Are we good? Are we good with that question?
I have a question. What did the exponent, it's just a little hard to, it's tiny.
Oh.
What did the exponent on the bottom of the first equation turn out to be? Go one up.
Here,
What is
this
that
one?
exponent?
It's 7/2. It's 7/2. It's this guy downstairs.
How did you get this
the one-
7?
Yeah, it's a 7. So it's negative 7/2, and then it became on the bottom positive 7/2. I put little strokes through my 7s. I don't know if that's a problem. That guy
so
is him. I can't hear what you're saying, Rachel. Your mouth is moving, but the sound doesn't.
Sorry.
Yeah.
If the 1/2 minus 6/2 would be 5/2, so I'm not clear.
Where's the 1/2 minus the 6/2 coming from? See, this here is negative 5/2. So when you
yes.
take 1 away from that, you take 2 more halves, and that's why this is now negative 7/2. Are you with me now?
Oh, I skipped the differentiation. Okay, I understand now.
Okay.
Here, I have one more question. Is there going to be a shortcut to find that answer?
No.
Oh, man.
The only good news is you don't get many like it. So it's not a typical question, right? We're kind of dealing right now, we've moved away from the kind of pretty obvious power rules to the really messy, ugly power rules. And on that same theme, here is a different ugly situation. It's not common, but it does happen. And it looks like this. And I need to rewrite anything that's here in a form that I can, a fractional power of t that I can use. Now this one here, I hope isn't too much an issue. Are you comfortable with that being called that? Right, a t on the bottom is that. Right, now have you noticed that all of this is inside the square root? Not just the 6, and it's not just the square root of t, it's the square root of 6t. So I'm going to put a little intermediate step here and call this the square root of 6 square root of t, right? You're allowed to split them. And that means I can call this the square root of 6 times, that's a 6, square root of 6 times t to the half. Now, all I've done here is get this original into a fractional power of t. Now we'll do the differentiation. Multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. So that's the differentiation done. Haven't we now got the style point problem, right? To make things look pretty. Fractional powers can be brought downstairs and made positive. Fractional powers can be brought downstairs and made positive. Have you noticed that I didn't really do anything with the numbers? You see that square root of 3 still on the top. Do you notice this one, which says a half square root of 6? Can't I bring the 2 downstairs and just call it square root of 6 over 2? Kind of looks nicer that way. Now, all I need to do here is, shouldn't this or both or none look like the original? And the only thing that is a problem was that that guy needs to be turned into the square root. And that is us finished. So a square root of 6 over 2 square root of t's, take away a root 3 over t squared. Are we good? One's a little bit less work than the one before. Put that over here. Here's the next fella. This question is not difficult. It just looks difficult. X to the power of 2.2. That's kind of weird. Plus e to the power of 2.2. This question, the derivative, can be done in one line. I don't need to change anything or alter its look or anything. I can do the power rule. Okay. Multiply by the power and reduce the power by 1. Would you agree the answer's ugly, but the original was ugly, so what's the deal? What's e to the power of 2.2? What's its derivative?
0.
Yeah, just another 0. Hey, isn't that a nice answer? Isn't it a lot quicker than you thought it might have been? Would you agree we don't care what the power is? Don't we just multiply by the power and reduce it by 1? All right. Okay, now I want to introduce, because we only have 5 minutes, a new function that we can find a derivative of. And so I'm telling you the answer, right? It's a shortcut. Here is f of x. It's equal to e to the power of x, right? Can you remember 141, the exponential function? You know, it's like 2 to the power of x, 10 to the power of x. Isn't e just a special number? It's roughly, if you want to know its value, 2.712. Right? Just like pi, right? 3.14 and stuff. The derivative of e to the x is e to the x. That is amazing, isn't it? But it's, you just trust me, because I'm telling you it's true, that the derivative of e to the x is e to the x. So if I give you a function and I call it 7e to the t plus t squared minus 1, and then I ask you to differentiate it, won't 7e to the t get you 7e to the t? It's one of my favorite functions to differentiate. Do you know why I like differentiating 7e to the t or anything that looks like that? Why do I like differentiating them? Anybody want to look into my head? Because it's easy. Isn't the derivative of 7e to the t just the same guy you started with? Isn't it kind of hard to screw up e to the t's or e to the x's, right? You can screw up any of the others because that will happen. And plus a 2t. Right, for the final question of today, here is one that is weird. E to the power of t plus t to the power of e. Anybody want to tell me what the derivative of that combination is? E to the t plus t to the e. Okay, let's do the easy one. What's the derivative of e to the power of t? My favorite thing to differentiate.
E to the t.
Yes, e to the t. God, you all thought that was a trick, didn't you? Now, if I asked you to differentiate t squared or t cubed, none of you would have second thought about it, right? You would have done the answer right away, right? If I said to you t to the half, wouldn't you use the power rule? If I said to you t to the -4, wouldn't you use the power rule? This is t to the e, right? T to the power of 2.712 and stuff, right? You can still use the power rule. What do I write down first?
E.
Correct.
E t. Would it be like e -1?
You nailed it. Wasn't that, well, I don't know, was that simpler than you thought it was going to be now that you see it? And you might say, well, E minus 1's kind of weird. Do we need to make it look prettier? No, that's as pretty as it's going to get. Leave it alone.
The only time that we can differentiate something with an exponent that's a variable would be with E. Is that right?
Oh, like the power is, yeah, yes.
Mhm.
Yeah, because normally, well, right now, yes, later on we'll show you how to do other ones. You're going to find out later, not today, how to differentiate those guys, because those can be differentiated as well. E is just a special version of that one, isn't it? Right, so those ones you can, right? Normally, don't you get to differentiate things that look like that, right? When they look like that, isn't it a power rule? But when they look like this, isn't it?